So in this section, we're going to talk about orthogonality, and more specifically, we will discuss orthogonal projections. So the key idea of this section is we want to find the closest vector y hat that sits inside W to the given vector y inside Rn. So let's look at this example. So suppose that u1, u2, and u3 is an orthogonal basis for R3. And let's say W be a span of the first two vectors. Then we can write any vector y inside R3 as the sum of vector y hat inside W and z inside the perp of W, or the orthogonal complement of the given set W. So we did this in R2 in the last section, but we want to generalize the similar idea in R to the n. So the situation is very similar. So you have a space W over here, and you have two vectors u1 and u2 that spans the given set W, and you have a vector y, which is an element of Rn. Then y hat corresponds to the orthogonal projection of y to W, so that is this vector. And z should be y minus y hat, which is given by this. So because u1, u2, and u3 is a basis for R3, we can write y as a linear combination of these three vectors. So this equals to c1 u1 plus c2 u2 plus c3 u3. And here the coefficients are given by y dot product with ui divided by ui dot product with ui. And we call this as the orthogonal coefficient or the projection coefficient for the given vector. And you want to keep this handy because we're going to use this over and over again. Anyways, W is spanned by u1 and u2. So we can tell that, well, this vector belongs to the set W. So you want to let this equals to y hat as an element of W. And this vector looks perpendicular to W. So let's let this vector equals to z. Then we will claim that z is in fact an element of W perp. Or in other words, z is indeed orthogonal to u1 and u2. And this is because if you take the dot product of z with u1, then this gives you c3u3 dotted with u1. And we know that u1, u2, u3 is the orthogonal basis, which means u3, u1 is orthogonal as well. So this equals to 0. And also, if you take dot product with u2, then again this gives you u3 dot product with u2, and that equals to 0. So we verified that z is perpendicular to every element in the given set W. And in fact, we can generalize this to n number of vectors. So in general, we can decompose any vector y inside Rn to be a vector inside W and a vector perpendicular to W. And if u1 through up is orthogonal basis of the given set or given subspace W, then y hat is given by the projection of y onto W, which is given by exactly the same thing as what we have above example, where z is defined by y minus y hat. And the point of this theorem is that this decomposition y into y hat plus z is unique, and we call projection of y onto W as the orthogonal projection of y onto W. So let's see why this has to be true. So we have to show two different things. First of all, we should show whether we can decompose y into y hat and z. So I will call that as the existence of decomposition. So we have W equals to the span of u1 through up. Then if you define y hat equals to y dot product with u1 over u1 dot product to u1 times u1 plus y dotted with u2 divided by u2 dotted with u2 multiplied to u2 and so on until y dot product with up, and the same thing for up's. Then you can tell that, well, this is the linear combination of u1 through up, so this is an element of W. Now, let's let z equals to y minus y hat. Then we know that the set u1 through up is an orthogonal set. We know that ui dot product with uj, well, if you take the dot product with two different vectors, then we should get 0. So this gives you, well, if you take the dot product with, say, u1, then that gives you, well, by definition, we have z equals to y minus y hat. And if you take the dot product with u1, then this equals to, so if you distribute u1 into the parentheses, then we have y dot product with u1 minus, so y hat is given above in this way. So we will get y dot product with u1 over u1 dot product with u1 times u1, and you take the dot product with u1 again, plus, and if you take the dot product with u1 and u2, then this gives you 0, so automatically the rest terms are equals to 0. Now we can cancel out these two, and that gives you the whole thing equals to 0. And likewise, if you run the same argument to u sub i's, then we get this equal to 0 for all i's from 1 to p. So for this reason, we have z is an element of W perp. Also, we have to show the decomposition is unique. So suppose that you have a different decomposition, y equals to, say, q plus w, where q is an element of w, and w is perpendicular to all vectors inside the uppercase W. So this tells you that we have two different decomposition of y. So y hat plus z equals to q plus w. Or equivalently, if you move things around, we have y hat minus q is the same as w minus z. So now, if you look at the left-hand side, well, y hat and q was an element inside w, so their subtraction is again an element of w. But on the right-hand side, w and z was an element of W perp, so they belongs to W perpendicular set. So here, note that there are only one vector that belongs to both W and W perp is a 0 vector. So we can conclude that y hat minus q and w minus z both equals to 0. So we get y hat equals to q and w equals to z. So this gives you the decomposition y into y hat, and z is in fact the unique decomposition. So let us practice to decompose the given vector into two different orthogonal vectors. So let's pause the video and try out this example before I give you the solution. Okay, so we have u1 and u2 is an orthogonal basis for w, and we want to write y as the sum of vector in w and a vector orthogonal to w. So in other words, we want to write y equals to y hat plus z, where y hat is given by the projection of y onto w, And this is defined by y dot product with u1 over u1 dotted with u1, and multiply this to u1 plus y dot product with u2 over u2 dot product with u2, and you multiply this with u2, and we have z equals to y minus y hat. So first of all, let us calculate the projection of y onto w. So y hat equals to, so if you take the dot product with y and u1, then that gives you 0 times 3 plus 3 times 0 plus 10 times 1 over u1 dot u1 equals to 3 squared plus 0 squared plus 1 squared. And you multiply this to a vector u1 that is given by 3, 0, and 1. And you do the same thing for the other side. So the numerator equals to 0 times 0 plus 3 times 1 plus 10 times 0. And you divide this by the magnitude of u, which is given by 0 squared plus 1 squared plus 0 squared. And you multiply this to the vector, which is given by 0, 1, and 0. So this gives you, I guess we have 10 in the numerator. And the denominator, 3 squared plus 1 squared is 9 plus 1. That equals to 10. And you multiply this to 3, 0, and 1. And you add this with, I guess 3 over 1 times 0, 1, and 0. So this gives you 3 and 3 and 1. Now for z part, we can get z by the definition on the top right side. So it is given by y minus y hat. That equals to, well, y equals to 0, 3, and 10. And y hat is given by 3, 3, and 1. So this gives you negative 3, 0, and 9. So we can decompose y into, well, 3, 3, 1 plus negative 3, 0, and 9. And the first vector belongs to w, and the other one belongs to w perpendicular. And you want to check that these two vectors are really orthogonal to each other. So check whether you get y hat dot product with z equal to 0. So geometrically, what we are doing is, so if you have w over here, and if you have the vector y that belongs to Rn, so the plane is w, and the whole space is Rn, then we have orthogonal complement w perp in this way. Then we decomposed y into two different vectors. So the first one is a vector inside w, which is given by y hat. And the other one is a vector perpendicular to w and parallel to w perp, which is given by z. And y hat and z's are orthogonal to each other. Okay, then we can ask a question. Like, what happens if y is in fact an element of w? So what if y is an element of w? What can you tell about the projection of y onto w? So geometrically, we can regard y hat as a shadow when you put the light toward the orthogonal direction of the given subspace w. So these yellow ones are light. Then we can tell that y hat corresponds to the shadow of the given vector y. So if your vector was in fact on the subspace w, then the projection of y onto w, or the shadow of y onto w, should be the same as itself, because the vector itself is kind of attached to the ground. Now, we want to approximate a vector y by using vectors inside a subspace w. So suppose that w is a subspace of Rn, and let's say y be any vector in Rn, and let y hat be orthogonal projection of y onto w, then y hat is the closest point in w to the given vector y. So in other words, the distance between y and y hat is the smallest among all the vectors in the given subspace W. So geometrically, if you have a space W over here, and you take a vector y that belongs to Rn, and let's say y hat to be the orthogonal projection of y onto W, and then whatever vectors you choose, like for example, like if you choose, say, this vector v, then you can see from the picture that the distance from y and y hat is smaller than the distance from y and v. This is way longer than the distance from y and y hat, right? So from here, we can tell that the distance from y and y hat is always smaller than the distance from, say, y and v, but the distance is given by the magnitude of their subtractions or their difference. So we get the desired inequality. And v is any vector inside W, which is different from the orthogonal projection of y into W. And in this point of view, we call this theorem as the best approximation theorem, and we will discuss more in detail in section 6.5. Okay, so suppose that y is given by this vector, and u1 and u2 are these, and w be a span of these two vectors. Then we want to find the distance from y to w. So let's pause the video and try out this problem before I give you the solution. So did you figure this problem out? So basically the idea is, well, the closest point to y should be y hat by the best approximation theorem, and the distance from y to w is the distance between y and the closest point that's inside w, so it should be y minus y hat. So we want to find these two quantities. So first of all, y hat is defined by, so we have y dot product with u1 divided by u1 dot product with u1, and you multiply this to u1, and then you take dot product, or you do the same thing for u2, then this gives you this vector. So the numerator on the coefficient, we have 2 plus 4 plus 0 plus 0, and you divide this by u1 dot u1, which is given by 1 squared plus 1 squared plus 0 squared plus 0 squared, and you multiply this into 1 1 0 0, and you add this with y dot u2, which is given by 0 plus 0 plus 0 minus 2, and you divide this by 0 squared plus 0 squared plus 1 squared plus 1 squared, and you multiply this to 0 0 1 1. So this equals to 6 over 2 1 1 0 0 plus, well, I guess negative 2 over 2 gives you negative 1 times 0 0 1 1. So this gives you a vector 3 3 and negative 1 and negative 1 as orthogonal projection of y onto the space W. Okay, once we have that, then we can calculate y minus y hat. Then that equals to 2, 4, 0, and negative 2 minus 3, 3, negative 1, and negative 1. And this equals to negative 1, 1, and I guess 1 and negative 1. So from here, we can calculate the distance from y to w, which is given by y minus y hat. And this equals to the square root of negative 1 squared plus 1 squared plus 1 squared plus negative 1 squared. Or this equals to square root of 4. Or in other words, we get the distance equals to 2. Okay, then what happens if the given basis is orthonormal basis? Well, if ui's are orthonormal, then they are like unit vectors. So the magnitude, or ui dot product with ui equals to 1. Or in other words, we don't have to write all the denominators for the projection coefficient. And furthermore, if you write U equals to U1, U2 through UP, so this becomes an orthogonal matrix. Then we can calculate the projection of Y onto W as U times U transpose times Y.